Alright, in this next example, we're going to be solving another trig equation. This one, 6 sine squared theta plus the sine squared, plus the sine of theta equals 1. So let me rephrase that, or restate it. 6 sine squared theta plus sine theta equals 1. I noticed a couple things right away. First of all, I have two terms with a sine in that, sine of theta. I also have this extra 1 hanging out on the other side of the equation. Now I also noticed that there's a square and a single power of sine. So the sines have different powers. Generally, when you have a situation like this, it's like solving a polynomial equation, right? Or a quadratic equation where you have like an x squared and an x in the same equation. You could almost think of this in the same way as you would the equation 6x squared plus x equals 1. It's a very similar structure to the equation. This is a polynomial equation, or a quadratic equation more specifically, that you would have solved in an algebra class using a variety of techniques. You could use completing the square, you could use factoring if it factors, and you could use a quadratic formula. This trig equation is a similar structure, except the x's are now trig functions, sine of theta. That's okay. We're going to solve it the same way that we would the polynomial equation. We're just going to use sine of theta as our variable, and then once we get sine of theta solved for, then we'll go and solve for theta using the inverse sine, or our whatever knowledge we have of the sine values that it's asking us for. Oops. Okay, so how would I solve, if I go to the polynomial version, how would I solve that? Well, like I said, there are three techniques. All of them would require you to, well, I guess not all of them. The two that we're going to really focus on are factoring and quadratic formula. In both of them, you need to get a 0 on one side of the equation. So let's start with that. I'm going to solve the polynomial equation, and then I'll show you the how it is analogous to the trig equation. So in the polynomial equation, I would subtract the 1 from both sides of the equation. That would give me 6x squared plus x minus 1 equals 0. And then I would factor. Now to factor 6x squared plus x minus 1, I would use something called the modified AC method. There's a variety of methods for this. The AC method is probably the most popular. I have a little tweak to the AC method that I've learned through the years and have found convenient to teach. And so I'm going to go ahead and use that. It's a little bit quicker, I think. The modified AC method is where you would take A times C, or the leading coefficient, times the constant. 6 times negative 1 is negative 6. And you would look for factors of negative 6 that add up to the middle coefficient. Okay, this is kind of the standard starting point for any of the processes. And in this case, it would be 3 and negative 2, right? Negative 2 and 3. Those are the two numbers whose product is negative 6, whose sum is 1. Okay, negative 2 and 3. I'm going to write that a little bit bigger. I feel like it's not real easy to see. Okay. Then the modified AC method does this. It puts two sets of parentheses up. This is going to be our factored form. The first term in each set of parentheses is going to be the 6 with an x. So I have 6x and 6x. Okay. The second term in each set of parentheses is going to be these two numbers. So the first one will be negative 2, and the other one will be a plus 3. Now, I don't want to forget my equals 0. That's an important part of this problem. Then, the trick on the modified AC method is that by putting a 6 on each of these terms, if you were to redistribute 6x times 6x is 36x squared, we have too many 6's. We have an extra factor of 6. And so, to get rid of that extra factor, I'm going to divide out any common factors in these sets of parentheses. So in this first set, there's a common 2, right? The 6 and the 2 have a common factor of 2. So if I divide out 2, I will be left with 3x minus 1. Right, I divided both terms by 2. In the second set of parentheses, they have a common factor of 3. So if I divide out 3, I'll be left with a 2x plus 1. Now if you think about redistributing this, 3x times 2x is 6x squared. That works. The negative 1 times the 1 gives us the negative 1 here. The other two terms, you know, the O and the I in FOIL, for instance, would be 3x times 1, that's 3x, and negative 1 times 2x is negative 2x. Well, 3x and negative 2x is 1x, which is that term in the middle. So it does redistribute properly. So these two factors are the two factors that I would be looking for. They are the correct factored form. And then, of course, you would take those two factors and set them each equal to 0 to solve. Right? So you'd have 3x minus 1 equals 0 and 2x plus 1 equals 0, and then you go through and solve that. Similar idea with the trig equation, okay? Except that instead of using x as the variable, you'll have sine of theta. But because everything is the same and I've already done all of this work, then I can just go ahead and jump right to this answer. In fact, what I would recommend is that when you guys are solving these factoring type problems, you could jump off to the side, solve the problem or factor it out, replacing the trig function with a variable, and then just substitute it back in. And so what we're really looking at here, if maybe I'll write out a couple steps though, is 6 times the sine squared theta plus the sine of theta minus 1 equals 0. So that's getting the 1 over. That's the first step there. Then I do my factoring. Now I'll skip all the details because I know all this is going to work out. And I would have, now this is going to look a little crammed, 3 sine theta minus 1 and 2 sine theta plus 1. Right, so instead of x's there, I'd have sines of theta. Then I take each of those factors and set them equal to 0. So I have 3 sine theta minus 1 equals 0, and 2 sine theta plus 1 equals 0. And so now I take each of those two equations and solve them individually. So here I would add the 1 to both sides. I get 3 sine theta equals 1. Divide out the 3. So sine of theta equals 1/3. Now we're looking for all values of theta whose sine is 1/3. Okay? This is unfortunately not going to be one of our nice special triangles. This is neither a 45-degree angle or a 30 or a 60 or a 90 or any of those. So we're going to need our calculators on this one, okay? Because 1/3 is not one of our common ratios that we're familiar with. So theta then is equal to the inverse sine of 1/3. So we'll go to my calculator, and I want to make sure I'm in the right mode. Now I said 0 to 2 pi. Okay, we're in radian. We need radians, right? So I'm going to go to radian. It's a little bit inconvenient, I suppose, on this one because we're not going to have any nice pi. It's not like going to be pi over 6 or something. It's going to be just an ugly decimal. So we'll just approximate these to, I don't know, 3 places after the decimal will be good enough for right now. So the inverse sine of 1/3 is a decimal. And let's see, 0.33, what's that, 98 roughly? I guess if I was rounding that to 3 places, like I said, it'd be 0.340, right? So that's approximately 0.340 if I round it off to 3 places, the nearest thousandth. Now, what's interesting here is that That's one answer. Remember though, we're looking for all answers between 0 and 2 pi. Well, the sign is positive. Well, what quadrants is the sign positive? First, second, right? The first and second quadrants. So, we found our first quadrant angle is a 0.34 0.34 radians. Okay, it's going to be up here somewhere. 0.340. And so what I now need is a second quadrant angle that corresponds to that. Okay, I need an angle over here that is 0.340 radians up from the negative x-axis. Well, you would take, to find that, you would take pi, which is at the negative x-axis, that's pi, and then subtract off 0.340. Okay, so I can do that. Now I'm actually going to do that without rounding. I'm just going to go on my calculator and hit pi minus, and then if you hit the second button, if you have a calculator similar to mine anyway, you hit the second button, and then the negative, it's the button down here on the bottom, the negative, that will subtract the previous answer from pi, and then hit enter. And there you go. So that's the second angle. It would be 2.802 approximately. If I again round that to the nearest 1,000. Okay. Okay, so that solves that portion of the equation. However, I still have a second portion, right? I'm going to need a little more space. So I'm going to clear off what I did in green on the right. Oops. If I push too hard, I'm going to knock my whiteboard down. A little sketchy there. Okay, so we'll take this one. Let's say I subtract the 1. I get 2 sine theta equals negative 1, and then divide out the 2. So I'd end up with the sine of theta equaling negative 1/2. Well, where is sine negative? Well, in the third and fourth quadrants. Okay? So what I need to do is go to my calculator and type in, theta is going to be the inverse sine or arc sine of negative 1/2. Okay, so I'm going to type in inverse sine negative 1/2. You could do 0.5 if you wanted. Now what's interesting is I come up with a negative answer, right? Negative 0.523, whatever, I'm reading that backwards. Okay? And that's kind of weird because that's not in our interval at all. Right? A negative answer isn't even in that interval. 5 to 4, I suppose, if I round that off. Round to the nearest 1,000. Okay? So this is not even in that interval. Remember, though, that the range for the inverse sine function, or this inverse sine, the range for the inverse sine is from negative pi over 2 to pi over 2, which is not entirely encompassed in this interval. So we've got to make some adjustments. We have a fourth quadrant angle, which is one of the angles we need. Right? I don't know exactly what it's going to look like, but it's down here somewhere. I need to figure out what that's going to be in the positive side, right? If I, instead of counting as a negative angle, wrap it around the other way. Well, I'm just going to take and add, let's just say 360, add 2 pi to it. Okay, that should work. So if I take this angle and simply hit plus 2 pi, there you go. That should give me the radians in the fourth quadrant with a positive angle. Okay, so add 2 pi, and you'll get theta approximately equal to 5.0760 if I round that to the nearest 1,000th. Cool. But again, that only gives me the first quadrant, or I'm sorry, the fourth quadrant, I still need a third quadrant because there is a third quadrant angle where the sine is negative. So we need the corresponding angle over there. Okay, how would I do that? Well, I need to take this original angle here and subtract it off, or add it to 180, 180 is pi, right? Oh my goodness, this is a little bit confusing, right? So if this angle here is the negative 0.524, then the angle down this way is also 0.524 further than pi. Okay, so you go around to pi and then keep going. So how do I get that angle back? Okay, I'm going to, I should have stored it maybe. I'm going to re-enter that inverse sine of the negative 1/2, right? Negative 1/2? Yeah. And then I'm going to change the sign of that. Well, how do I make that a positive? I just hit the negative, and then I hit second negative again to get my answer. So it'll say negative answer, and it will change the sign. Pretty good. And then I'm going to add pi to that. So a little bit of calculator work. 3.665. Okay. That will be the fourth angle in question. All right, so now I've got a first quadrant angle and a second quadrant angle corresponding to the thetas that make sine 1/3, positive 1/3. I have a fourth and third quadrant angle corresponding to the angles that make the sine negative 1/2. Now the last step is our solution set. Okay, we've got to have a solution set. Well, our solution set then, I just got to list these off. 0.340, 2.802, 3.665, and 5.760. Now I'm guessing most of the time, if my math lab if you were doing this on my math lab, they would probably have had you do this in degree mode rather than radian mode. Sometimes the angles just make more sense that way, and I'd be okay with that, unless it was asking specifically for this. If it was asking specifically for 0 to 2 pi interval, then you got to do the radians. I think in this example, the degrees would have been easier, but you know, that's how we started it off, so that's how we finished it off. And you know, it's good practice to see how radians do show up, and sometimes we don't have the exact values with pi's in them for all the radian measures. Sometimes they're just going to be difficult decimals to work with, but they will work out. So, okay. Anyway, don't forget your solution set, and that's a nice answer right there.